Hello, and welcome to our project entitled Pure Rocket Power. In this project, we'll be measuring the performance of homemade model rockets my partner, Alex Neff, and I made all by ourselves. Just a little bit of background, me and Alex have been making homemade model rocket engines for about 2 years now, and this project is actually kind of an extension of last year's project in which we made homemade model rocket engines and model rockets. As you can see from this video here, it didn't turn out too well, and we believe that's because our model rocket engines did not produce enough thrust to allow the stability fins to work and for the rocket to gain altitude. Instead, it just crashed into the ground. So our project this year was focused on gaining more thrust out of our engines.
So to gain more thrust, we first had to measure how much thrust we were already doing. So we did some research and we found that there was certain performance indicators, which are sort of like metrics used to measure the performance of a model rocket, like average thrust, maximum thrust, and impulse. We'll talk about more what these actually mean later. But the point is that all of these metrics are derived from the force versus time graph. So the objective of this project was to measure the force versus time graph. So our solution was to create a rocket cart, as you can see in the right there. So with video analysis, which we learned in our physics class this year, we can get position over time by going frame by frame through the video. From that data, we can derive the force over time graph. So the rocket cart just works like this. We take a video at this angle that you're seeing it now, and after 1, 2, and 3 seconds and everywhere in between, after every frame, we can tell the position of the cart. And this allows us to get acceleration of the cart. So to get force over time, we need to get mass and acceleration because that's what equals force. So as you can see in the bottom right, through all this math with like free body diagrams and stuff like that, we derived that the acceleration of the rocket, a sub r, is equal to the acceleration total, which is measured with the video analysis that we use, plus the constant acceleration that is against the rocket cart from gravity. So using that, we can get acceleration. To get the mass, it's not as simple as just measuring the mass of the rocket because the rocket actually is throwing mass out of the back of it throughout the whole burn. So as you can see in the bottom there, throughout all this math, we determined an equation for the mass at any given time, m sub t, is equal to the mass of the initial rocket minus the m dot, which is the mass flow rate, which is how much mass is thrown out every second, times time. So with that, you can get the mass. So combining these equations by multiplication, you can get the force over time, as you can see in the green box there.
So Alex and I decided that the first step of this project would best be building the track for the rocket cart and the homemade engine. We went through a couple ideas like building model train tracks, that sort of thing, and just sending a rocket through a big PVC tube. But in the end, we settled on cutting a 10 feet PVC tube in half and using the two tubes as sort of like divots for the wheels and guiding the rocket cart along its path along the 2x6 piece of lumber we used as a ramp. As you can see in the top right, that's sort of a diagram, and the next picture will be our actual setup. Now, what entails a model engine? It's really simple, actually. There's just two clay end caps that hold the propellant inside. There's a nozzle drilled into the bottom end cap to allow the release of the rapidly expanding gases from the lit propellant. There's the propellant inside of those, and then there's the casing that holds all of these ingredients together. Making our own homemade engines was actually pretty simple too. We just cut a PVC pipe for a casing is around 2.5 inches usually. Then we used wet clay for the bottom end cap, and we used a ramrod as shown on the right diagram, and we compacted that. Then we added propellant. We used the ramrod again to compact that. Then we added more wet clay to form the top end cap, and we compacted that. After we waited for it to dry, we drilled a hole through the bottom end cap and all the way through the propellant. Now this is actually kind of important because if we didn't do that and just lit the propellant, then it would burn kind of like a fuse from bottom to top and very slowly. Now, by drilling a hole and lighting it, it burns from the inside out all over, and that increases the burn rate, which increases the thrust. Now, this is a diagram of the inside of a model rocket engine as it's burning. As you can see on the right, there's rapidly expanding hot gases. In the middle, that sort of molten orange thing is going to be the propellant. And to the very left and the very right are going to be clay end caps. Let's talk about propellants. S-type is just a fancy name for sugar. Um, see, in this propellant, sugar is the fuel, and potassium nitrate is the oxidizer. Sugar is what actually burns, and potassium nitrate provides the oxygen for it to burn. Now, in black powder, sulfur is the catalyst, charcoal is the fuel, what actually burns, and potassium nitrate is going to be what provides the oxygen. Black powder burns more, faster than S-type, but actually granulated black powder burns even faster than both of those. Now, to make granulated black powder, you need to soak black powder in rubbing alcohol to more thoroughly mix the ingredients, sulfur, charcoal, and potassium nitrate. Then you break that into small pieces and let it dry. Now, as a general rule for propellant mixes, the smaller the particles of the propellant and the better mixed it is, the faster it's going to burn and produce more thrust. This is a video of our sugar mix burning, our S-type fuel. This next slide is a video of our black powder fuel burning. As you can see, it burns a little bit faster. And this next slide is going to be a video of our granulated black powder propellant burning. It's the fastest of them all.
So to light these propellants, you don't exactly want to stick your hand with a lighter behind the lit rocket engine. So we use these remote electronic igniters where through the alligator clips, we run run a current through the filament. You can see at the top there above the black tape. And because the filament's very thin, it actually heats up and lights the propellant, as you'll see in the video.
So for test one, we decided to start out with a sugar mix propellant. We also used our first iteration of the rocket cart, which weighed about 540 grams, and our first iteration of the rocket cart track, in which we just glued one half of the 10-foot PVC pipe onto a 2x6 piece of lumber. As you can see from the video, the problem was there wasn't nearly enough thrust to move the cart. So we decided to make a lighter rocket cart, around 360 grams, for our next test. That was also a failure. And what happened here is the end cap popped out, there wasn't enough thrust to move the cart, and our tracks fell off. So we decided to glue the PVC pipe back onto the 2x6 piece of lumber and use a more powerful engine to decide whether the problem was our rocket cart or our engines. Now, in this video, you'll see that the commercial engine that we bought, the Estes D12, proved to be way too powerful for this iteration of our rocket cart. So we decided that the problem was actually our propellant. So we used regular black powder as a propellant for this next test. And as you can see from the slide, it was a total success. In the video, it just goes cleanly up the ramp, and this can definitely be used for video analysis of the thrust of this model engine. Now, in test 5, because we have to test different types of propellant, we use granulated black powder. We named this engine Glenn, and not Glenn, Gerald. He was a failure, I'm sorry to say. We also moved where we tested onto Alex's driveway. See, the problem here was there was too much thrust and the rocket flipped, and also the track fell apart again. So we decided to weight the cart with rocks to counteract the thrust of the granulated black powder, lengthen the wheelbase of the rocket cart to make it more stable, and use countersink screws to permanently adhere the PVC pipe onto the 2x6 piece of lumber. Now, in our next test, test 6, we named him Leon. It was also a failure, I'm sad to say. This time we used regular black powder. And you see the bottom end cap of the model rocket engine actually popped. You'll see that in the explosion about halfway through the video because it wasn't strong enough. So we decided to wet the clay before compacting it, and this would make it stronger, more concrete-like. This is just a fun picture of the explosion that happened. We thought you'd like that. Now on to test 7, Neil. Total success. We used regular black powder in all our previous adjustments, and there were no problems. He went smoothly up the track, and we could definitely use this for video analysis. Now, test 8, I'm sorry to say, Janky G was a failure. We used granulated black powder, and funny enough, it happened again. The bottom clay end cap actually popped out and wasn't strong enough to hold, as you can see from the explosion about halfway through the video. So this time we decided to use a layer. We decided to add layer by layer wet clay onto the end caps to make them stronger and add more weight to the rocket cart to counteract the increased thrust. Now for Janky G Jr., he was also a success and used granulated black powder. All our previous adjustments were used, and this could definitely be used for video analysis. On to test 9. Test 9, Glenn, he was a failure. He used black powder and all our previous adjustments. And again, the bottom clay end cap blew out. But this time it was due to us drilling too small of a nozzle to release the gases. They couldn't be let out in time as the propellant was burned. So it popped out. So we decided to switch back to a normal nozzle diameter. Test 10, we named him Apollo. Total success, regular black powder, all our previous adjustments created the perfect storm in conditions. Test 11, our final test, Artemis, was also a success. This time we used granulated black powder, and as I said, all our adjustments created the perfect storm of conditions to allow it to go up the ramp.
So when analyzing these 4 successful tests, we had a lot of failures and we had 4 successful tests. We had to have something to compare the data against. So we went with the Estes D12 motor, which is a very similar motor, which is why we went with it, because it's 45 grams and 2.75 inches, which, as you'll see, is very similar metrics to our engines. And it has these data points. The max thrust is 30 newtons, as you'll see at the very peak there on the left. That's the classic commercial engine has this sort of shape of a force curve. It has one very high peak of max thrust, and then it trails off into more average thrust. As you see on the table there, the average thrust is 10.5 newtons. The maximum impulse basically is the power rating. It's the area under this force versus time curve shaded in gray, and it basically it means that it's basically a power rating for your motor. So your motor could either last for twice as long and burn half as strong, or it could burn twice as strong but half the time. So that would be the same impulse. So for Neil, our first successful tests, you can see the purple force curve on the left there is actually pretty close to the shape that we see in the other more official commercial motors, and the data actually reflects that this motor outperformed the STD12 in every single metric that we measured. So it was a little bit heavier and it was a little bit shorter, but its max thrust was almost 9 newtons more than the D12. It had almost 4 newtons more on the average thrust side, and its impulse, which is basically like the power rating, was 16.01 newton seconds, which is basically average for a D12.3 because the D12.3 maximum impulse is 20 newtons. It's not always 20 newton seconds. So the data for our second successful test, Janke Jr., is listed here. You can see the force curve is a little bit uglier here. It didn't burn as smoothly as Neil did. But in the performance indicators, it shows that ours was a little bit heavier. It was 4 grams heavier than a standard D12.3, and it had a lot lower max thrust, but comparable average thrust though. Its impulse, though, as you'll see with this test and later tests, was pretty bad at 7.83 newton seconds. Not very good power rating. Next, we have data on Apollo. You can see the force curve is a little bit messed up here. It has that max thrust sort of peak, but then after that, the trail off to the average thrust is kind of unusual. We're not sure what the negative blips there are, where the force goes into the negative territory. But the data for the performance indicators show that it was a mediocre engine. Its average thrust was less than expected, but its max thrust was pretty high, and its impulse was not bad. We noticed that the BP motors, the black powder rate motors, as opposed to the granulated black powder motors, actually performed better. So Apollo and Neil performed better than Janke G and Artemis did. We're not sure exactly why this is, because we thought that the granulated motors would actually burn better, but that's what the data shows, is that the regular black powder burns more efficiently. So like I said, Artemis is a granulated powder motor, and the data is shown here. The force curve is there. It's a little bit messed up. It's kind of got these 2 peaks, and we think that's due to like some uneven compaction of the propellant inside the rocket, because even in the video you can see there's flickering sort of the propellant burn. So we think that's what caused that. But the performance indicators show that it wasn't a great engine. Its impulse was very low. It was actually the same as Janke G Jr.'s was, and its max thrust was mediocre, and its average thrust was actually pretty good at 11.66 newtons. So in conclusion, looking back on this project, me and Liam think that we probably should have measured and recorded things better, took more careful detailed notes of things. We think this could have helped us in determining what should change between tests. We were kind of lost at points where we were kind of throwing darts in the dark as to what we should change to make the thrust higher and the failures less prevalent. And we also thought we should take more time with our parts and do things with higher quality. As you saw, a lot of our caps blew out because of not paying attention to them enough, not layering the clay enough. And as you saw with Artemis, the propellant was unevenly mixed, so it sort of created that flickering. And with our track, it was actually hot glued at first, which was not a good solution. We eventually screwed that down, which was a much better solution. Looking ahead with this system, we'd actually like to do a few more things with it. We could check the accuracy of this analysis by using commercial motors. So basically, we would buy some commercial motors and check our force curve versus like the commercially available online force curve to see if our analysis is accurate. We'd also like to use this method to predict the altitude of a rocket that we make. That we think that'd be pretty cool if we could just sort of match up the altitude with a prediction on the ground. So yeah, that was our project. Thank you for listening, and see ya.